kind of keep going infinitely wide until you can't see them?
Out to 90 degrees, yes. So, what we're going to talk about is called Fraunhofer diffraction. Fraunhofer diffraction is looking at the interference between light rays when you're far away from a slit or an opening. Fresnel interference, or Fresnel diffraction, is when you're closer. Fresnel, while I like the name Fresnel better, it just sounds nicer to me. It's the harder one mathematically, and we're not going to be doing that. It requires some more complex math. So the setup of how we do these problems is we have light going through slits. Now in this picture, I have coherent light. What does it mean to be coherent? All in phase. Okay, so I have coherent light that's coming and going through, in this case, a bunch of slits. So it's like the last example I did. We're going to start our problem with dealing with just going through 2 slits. And then we'll talk about what happens if we put more slits in lab this afternoon. So we have coherent light that's coming through the slits, and the light has different path lengths to get to some point on the screen. For instance, if we take this position that's labeled P, the light from this slit does that distance. The light from the next slit does that distance. And clearly, the second one I did is a larger distance than the first one I did. And if you have a different distance, that means it's going to take a different time for the light to get there. And if it takes a different time to do that different distance, that means that they're no longer going to be in phase. Their phase is going to vary based on the difference in the distance. And so it's that variation in phase that is the key to understanding how diffraction works. So let's set up a problem. First of all, we're dealing with electric fields, and so we have sinusoidal electric fields. So the electric field strength is E0, the strength of the electric field that goes through a single slit, multiplied by sine of omega t plus phi. Omega, what does that omega stand for? It's the angular frequency. So omega is 2 pi f because it's in radians, whereas frequency is in cycles per second. And then this angle phi right here is your phase angle. And we will just arbitrarily say we're going to set our time equals 0 so phi is 0. Right? Because that's just, depending on when you set time equals 0, you get different values for phi. So you just arbitrarily say we're going to set our time 0 so that phi is 0. So that gives us a slightly simpler way of writing the electric field oscillation like that. Now I am not positive if I have this on the next slide or not, so I'm going to say something now. If it's on the next slide, we'll just gloss over it. The intensity of light is equal to the, well, it doesn't have to be average. It's the power per unit area. And that intensity relates to what we actually see. If there's more power being delivered per unit area, we see more. And so what we really care about is the average intensity, which is if you take the average over one cycle, so over one period for our light, and average the intensity. Now, the intensity is proportional to the electric field magnitude squared. So as we go through these things, we're going to be calculating electric fields, but then once we have the final electric field, we're going to square it. We'll throw away negative signs after we've squared it, because it's the magnitude. By the way, just if you're working with real numbers, when you square it, it's always positive. If you're doing imaginary numbers, you could have a negative, but that's why we have the absolute value sign. And yeah, you may have taken a class where you learn about the mod squared. That's what this actually means, the mod squared. You take the complex conjugate times the original, multiply it together, you always get the magnitude. Okay, so we're going to find the electric fields, and then we're going to square it to find the intensity, and then take the average over time to find the average intensity, which tells us how bright the light's going to be. So when we looked at those patterns at the beginning of class, you saw places where it was bright, that's where the intensity was high. Places where you couldn't see it, intensity was low. All right, so now we see if it's actually on the next slide. No, it wasn't. Good. Next part. For the light to go from my slit to the screen, it's going to take some time to get there. And the time depends on how far it is to the slit, or from the slit to the screen, and the speed of light. So we just use our equation, relates time, distance, and speed. That is, the speed is equal to the length traveled over the time it takes. Solve that for delta t, and instead of putting in v, we put in c because we're doing it in vacuum, or in air, because air is essentially the same speed as vacuum. And so that's all we have there, is we're going to plug in the time from when the light hit the initial grating. Remember, I had the collimated light coming into the grating, or not collimated, the coherent light coming into the grating. The time that it takes to get from the grating to some specific point on the screen is delta t. And as I said with the first picture, that delta t is going to depend on which slit it goes to and where we're hitting the screen. So if I substitute this delta t equation into my electric field is E0 sine of omega t, well, here I put in this delta t in there, and delta t is going to be, well, the total time is t plus delta t. The time it was when it hit the slits plus delta t, the time it took to go from slits to the screen. So this is actually, it seems odd to have t equals t plus, but this t here is the time when it hit the grating, and this t here, so that's the time of the grating, and this t here is the time of the screen. So that's, okay. I see as I'm looking at this that it could be more confusing. I'm trying to straighten out that confusion and probably making it more confusing yet. We have okay, that's the equation for our electric field as the wave is traveling. And so we said the time at the screen is equal to the time at the grating plus delta t. The delta t I calculated at the top of the page is the time it takes to go from the grating to the screen. And so we put this time for the screen in, the time when the light gets to the screen. And so putting all of that in together, have two terms here, multiply through, so you just see the omega was distributed, and then make the substitution that since omega is 2 pi times frequency, and you can see I already wrote it in there, that omega divided by c is 2 pi times frequency over c. But by definition, frequency divided by speed of light is 1 over wavelength. And so we can replace omega over c, this right here, with 2 pi over the wavelength. And now a person might ask why you want to do that. Just because you can doesn't mean you should, right? I can go run in traffic, but I shouldn't. So the reason I do that is because now I have an equation that tells me that the electric field at the screen is equal to electric field that I had at my grating multiplied by sine of omega multiplied by the time at the grating plus 2 pi times the length between the point it went through the grating to the point it went to on the screen divided by wavelength. So this here is the part that is going to vary depending on where you're hitting the screen. That length is going to be different depending on where you're hitting the screen. And so that's why I wrote it out this way, because that length now is geometric. We can use geometry to find the length. Everybody with me?
So if the grading was like right at the length source, then you could just have that be 0, right?
If the grading was right at the screen, the place where we're going to view the pattern,
Okay.
then the length would be 0. But then we'd be well into the Fresnel range, right? Fresnel is when you're close.
Gotcha.
And we're not doing that because that's much harder. And you look at what we do and you don't say, oh, that's the easy stuff. But just consider that compared to the other stuff, it is the easy stuff. Okay, so now we have 2 slits. Right, because I said I'm going to start with a double slit. I have light go through 2 slits. So it's the in-phase light. So I have E0 sine of omega t plus 2 pi L over lambda for both of them. But I have L1 and L2 because you go through 2 slits. It's going to be different lengths to get to the same point on the screen. And so I have to add those 2 together. And on my slide from last year, I corrected it now, but I had already put it on my tablet before I noticed the error. I had my sine and cosine in the wrong places. Let's show how we go from this equation to that equation, shall we? Okay, one person said, sure, why not? Or gave me a double thumbs up. So we have a trigonometry identity that says sine of A plus sine of B is equal to 2 times cosine of the difference in A and B divided by 2 times sine of the sum of A and B divided by 2. That's where I had my mistake. I had the cosine and sine in opposite positions. So we just take these, and if I take these 2 arguments, so let's just call this A and call this B, then A plus B over 2 is equal to, if you add those together, you're going to have omega t plus omega t, 2 omega t. And then I have 2 pi L1 over lambda and 2 pi L2 over lambda, so I can factor out the 2 pi over lambda. So there's the sums, and now I divide by 2. So that's A plus B over 2. If we simplify that, 2 omega t divided by 2 is omega t. 2 pi over lambda divided by 2 is pi over lambda. I keep writing English L's instead of Greek L's. So there's what we get with A plus B over 2. So that's what we should have for the argument of the sine. Got a question? Okay, now let's look at A minus B divided by 2. So A minus B divided by 2, come up here so we can see what A and B are. Come on, don't jump. If we look at A and B, they both have omega t. So I'm going to have omega t minus omega t, which is beautiful because then time disappears. They subtract out. And I'm left with, I can factor out 2 pi lambda again. I'll have 2 pi L times L1 minus L2. And then, of course, I have to remember to divide by 2. So that's equal to and so we look up pi over lambda times L1 minus L2. Now you look at my answer and their answer, and you notice a difference. What's the difference? Here, pi L2 minus L1 over lambda. Here, pi over lambda, L1 minus L2. What's the difference? Yeah, one is minus the other. And you might say, oh, Richard made a mistake. But you'd be wrong. You'd be wrong because we had sine A plus sine B. And then we take the difference. Does it matter which one's positive or which one's negative? There's no way to differentiate them. So it has to be the same either way, and indeed it is. because cosine of minus theta is the same as cosine of plus theta. So our answer is equivalent. There's no difference in the value. Yes, I scroll up. Scroll down. I can scroll all around. Got these skills. So how is this helpful? Remember when I started, I said we're going to work with the electric field, and then we find the intensity by taking the electric field magnitude squared. And so now I have the electric field of the two combined, and the intensity is proportional to that thing squared. And then the average intensity is going to be the average over one cycle. So if we look at this, let's go ahead and do that. We're going to have nope, that's this one right here. There's our electric field. And now we square it to get our intensity. Now it's important that we remember intensity is not equal to electric field, it's proportional. So the intensity is proportional to the electric field squared. Well, the electric field squared is going to be 4E0 squared, cosine squared, so that's going to tell me what my intensity is at some moment. And then I need to average it over one cycle. Now, where does time appear in this equation? Only in the sign. So this here is a constant. So that's just going to drop down. When I do I average, that's just going to come down as is. And then I have to take the average of sine squared. What's the minimum value sine has? Okay, I should have asked what's the minimum value sine squared has, and then the answer is 0. Because that's where average is sine squared. What's the maximum value sine squared has? 1. And what can you tell me about the shape of the sine curve? It's sinusoidal. It's nice and symmetric. Where's the average going to be? Halfway between. Because of its symmetry, the average is halfway between 0 and 1, which is 1/2. So this is going to be 2E0 squared cosine squared pi over lambda L1 minus L2. That's my average intensity is proportional to that. Because it's proportional, we just say, let us call this right here, let me change colors for the final, I max. And so we'll just say that the I average is equal to I max times cosine squared of pi over lambda times L1 minus L2. Now we are not done, but what we have now is an equation that tells us how the intensity fluctuates as a function of the distances from each of my two slits to a single point on the screen. So now the next thing is to find the geometry for those distances. So there was no calculus involved, right? And in fact, it was trigonometry, adding the sines was the hardest thing. We're going to get to some when we go to a single slit. So for our double slit, in the far field approximation, in the Fraunhofer region, we have two slits that are close together with a screen that's much farther away from the slits than the separation between the slits. If that's the case, then this triangle of the light that leaves one slit and hits point P and the light that hits the other slit and hits point P is essentially like this. This angle here is 0, approximately, right? Because we're far away. And if it's triangle and that's 0, if I cut it like this and make this a 90-degree angle, then what's the other angle? 90 degree. So this is your classic 90-90-0 triangle. That's the approximation. That's the Fraunhofer approximation. In reality, it's obviously going to be more like 0.001 degrees and 89.9995 or whatever it adds up, right, for each of the other two. But that's close enough to 90-90 for us to say, okay, we're going to make an approximation here and run with it. So in that case, the difference in the path lengths is just the difference from here where I had to square it off to get those 90 degrees. And so if I call this angle between my plane of the slits and the line I had to square it off, theta, then I can just use, once again, my definition of sine, cosine, and tangent. Which side of this triangle is D? Of this triangle right here, which side is D? It's the hypotenuse. So D is equal to the hypotenuse. And then this side here that we're looking for, which side is that? Opposite. And so our delta L is the opposite. We know the hypotenuse, sine theta, is equal to the opposite, delta L, over the hypotenuse, D. And so delta L is just D times sine theta. Of course, what is that theta, you ask? Right? I introduced this angle theta, I just moved my problem off one step further. Well, that theta is actually pretty simple, because just using trigonometry, the angle between the line that goes normal to the slits to the screen is going to have the same angle from the line going from my slit to the screen, the light path, as I use in that triangle. You can see this is a right angle here, this is a right angle here. And so the angle between this and this is the same angle. Not seeing it? No. Okay. Let's look at this then, erasing the stuff I did before so we can look at that carefully. I'll zoom back in. So I have a right angle here. And then I have this line. So I'm looking at the angle between this line here and this line here. Now if I take a perpendicular to the blue, there's perpendicular to the blue. And if I take a perpendicular to the red, here's perpendicular to the red. And so this blue and this red are perpendicular to this blue and this red, hence the angles between them have to be the same. So that means that, is there a question over here? Okay. That means that what we do is we use the angle of our viewing, the angle to the screen, as our one variable, and then we know delta L is just d sine theta. Well, delta L is L1 minus L2. So from the previous page, I had I is equal to I max cosine squared of, that's not a pi at all, pi over lambda. I'm not sure if I had L1 minus L2 or L2 minus L1. Like I said, it doesn't matter because it's the same answer. And so this here is just delta L, which is equal to d sine theta. And so I get the equation then that I is equal to I max cosine squared pi over lambda times d sine theta. Now this tells me how the intensity fluctuates. So what angles, what arguments for cosine squared are going to give me 0 for intensity? What angles give me a cosine equals 0? Cosine of what equals 0, friends? Okay, cosine of 90 degrees is 0. Cosine of what else? Negative 90? So plus or minus pi, putting it in radians, or what else?
Pi halves.
Yeah, pi halves, thank you. Or what else?
Or 3 pi over 2.
Plus or minus 3 pi over 2. One more. Plus or minus 5 pi over 2. Now we can just make a pattern then. That's equal to m plus 1/2 pi for m equals ... minus 3, minus 2, minus 1, 0, 1, 2, 3, ... Right, for any value of m, if I put in m is equal to 0, I have 1/2. If I put in m is equal to 1, I have 3/2. M is equal to 2, I have 5/2. M is equal to minus 1, I have minus 1/2. So that function encompasses all of them. So for any integer value m, positive, negative, or 0, then this is going to be true. So my condition for 0 intensity is going to be pi over lambda d sine theta is equal to m plus 1/2 pi. Clearly I can cancel something here. And we usually write this as d sine theta is equal to m plus 1/2 pi. Or pi, lambda. Now in this equation, what is d? D is the separation between the slits. What is theta?
Between normal to the slits and the angle slits, or the direction lights going.
Okay, she defined it very clearly. I named it the observing angle, but it's exactly what Tori verbalized there. Right? You have to know what your observing angle means, and it's the angle between, I'll go back to the picture so you can see what she was talking about, the angle between the line that goes from the center between the slits to the screen and the line that goes from the center between the slits to the observing point. That's how we define the theta. And then the final thing, of course, we have m is a counting number and lambda is the wavelength. I'm not going to spend time on those because you're pretty clear on those. So these were the conditions for 0 intensity. Those are where we have dark regions. What about for where we have bright regions? What would change about my derivation if I have a bright region instead of a dark region? I would need to find when cosine squared is a maximum. So what angles give you a maximum for cosine squared? If it's maximum for cosine squared, what is it for cosine? or negative 1. So we're looking for the angles that would give us 1 or negative 1 if it's going to be a maximum. What angles give us 1 or negative 1 for cosine? 0, pi, 2, any integer multiple of pi. And so for constructive, interference, what kind of interference gave us 0 intensity? Destructive, right. Interference, we need pi over lambda d sine theta is equal to m pi, where m is just an integer. Positive or negative integer. And so once again, I can solve this to quickly get d sine theta is equal to m lambda. So there's my constructive interference case, the destructive interference. Was for half integers. What if I was at some angle other than those two angles we specified? What if cosine theta equals 1/2? Then what kind of interference do I have? Yeah, it's partially constructive or partially destructive mixed. Right, so I'm not going to have 0 intensity if I'm not on the constructive one. I only have 0 intensity if I'm right on the destructive. I have maximum intensity if I'm on the constructive one. So now you can take this equation and you can plot it as a function of angle, which I believe I have on, okay, I would just add a slide. I believe I have, nope. I have it for the answer after the second part. But you can plot it and you have the intensity does something like this, getting biggest at the center and then going down on either side. The spacings in terms of angle are, equal angles. On the screen, since on the screen you're looking at the opposite side of a triangle, if the angles change equally, the spacings are not going to change equally on the screen because you have to use, tangent to convert from the angle to the distance on the screen. And so I'll worry about that tangent part when we talk about it in class this afternoon or in lab this afternoon. Any questions about that double slit interference derivation? There was 0 calculus involved. We just added up light that started out coherent, going through 2 slits, and coming together at one point on a string. And our method was calculate the electric field of the screen, and then square the electric field. The intensity is proportional to the square of the electric field, and then take the average over a period to find the average intensity, what our eyes would see. Now we're going to do that same thing, but instead of doing the double slit, the single slit. Right? That's what I started with when I showed you illustrations. I started with a single slit. Now the single slit, we can treat it like it's a whole bunch of little tiny slits. So like it's an infinite number of slits, each separated by an infinitesimal amount. That's where calculus comes in. Because just like before, we're going to go through the same strategy. We're going to add up the electric field at the screen, do the light coming from each one of those slits, and then once we've added up the total electric field, we'll square it and say the intensity is proportional to this, and then we'll find the average over time. So now we're going to have to do some integration. But the integration is done graphically, not mathematically. That is, you're not using an integral table or anything like that. You're not integrating a function. You're integrating graphically to see what it's going to add up to. So how do we do that? First, that breaking the slit up into an infinite number of tiny slits. So we break it up into a capital N number of slits. Each slit then has a width of the total slit size, which varies depending on which picture I put up there. On this picture, it's a capital D. On the next picture, it's a lowercase a. Different sources use different symbols. But you're going to have each one of these little tiny slits has the width of the total slit width, which in this picture, like I said, total slit width is capital D. And on the next page, it'll be the total slit width is lowercase a. So I'll just put equals lowercase a so we don't have that confusion. And then each one of those is going to have a slightly different path length to get to the same point on the screen. And so just as we did before, we would have the electric field due to the nth slit is going to be the electric field divided by the width of the number of slits you have. So the total electric field going through the hole divided by the number of slits. So that's the electric field strength that went through just your slit, times sine of omega t plus 2 pi L over lambda. But what is L? Well, L is different for each slit. And so I've broken the L up there into 2 pi L0 over lambda. L0 is the distance from the nearest point to the slit, or to where we're going to view it on the screen. So that's what L0 is. Any other point has a longer distance it has to travel until the last one up here at the top has to travel a maximal distance of, just using your geometry here, it would be a sine theta is the amount that that last one would have to travel. That's more. And so I take that total of a sine theta for distance, divide it by the total number of slits, capital N, and that tells me how much more each slit's path length is going to be. And then for the nth slit, it's going to be n times that incremental increase, lowercase n. And so this lowercase n is the phase change, which is, that's the phase change per, or the path length difference, excuse me. Well, actually, using beta, it is phase. So a sine theta over n is the path length difference per slit of these infinite number of imaginary slits I made. And beta is defined up there at the top. Beta is just taking that path length and doing the multiplied by 2 pi over lambda to get it into a phase, to get into an angle. And so I have this here is the path length difference per slit, and so beta over n is the phase difference per slit. And so then you just multiply that by lowercase n, so for the nth slit you have that much change in phase. Now this here is in the form of a phasor. Remember with electricity, when we had AC circuits, we did phasors where we had the voltage across this inductor is V max sine of omega t plus phi, where that phi was a phase angle. And then we made phasor diagrams in lab, and we found that the total voltage was just found by summing those phasors, adding them as vectors. Well, hence the term phase vector. That's what we're doing here. Each little slit allows the same amount of electric field through, the E0 divided by n. But the phase angle is slightly different. And so we just start adding those up. So this picture here, if you see the little arrows, actually I'm going to zoom in again. I think it's better to see this zoomed in. If you note the little arrows, those little arrows are for if you did a discrete number of slits. You know, like I broke it up into 10 slits. And then I add up the phase vector for each of those slits. And then going from where I started to where I ended tells me the total electric field. Well, if I'm doing it for an actual opening, I have to have an infinite number of slits. And so the red is having an infinite number of slits, and then you have a nice perfect circle, or a perfect arc of circle. Now we're going to have to use geometry to figure out how this helps me. Yes?
Wait, what's the arc represent?
The R is in the end
Oh no, the arc.
of the arc. Okay. You have electric field that's coming through this, right?
Yes.
And so the total electric field that comes through there is going to be the length of the arc. But when you get to the screen, because you have different phases, right, because it would all be flattened out. If you're right here, it would just be a straight line and adding them all with the same phase angle. But when you get to the screen, they all have different phase angles. So you have just going from here up to the top, and it's better illustrated in the next slide, but going from here to here, that's the electric field at the screen. You take that squared, and that's going to tell you the intensity of the screen. You take the length of this arc squared, and that tells you the intensity of the light that comes through the slit. So we're going to have to use just trigonometry to relate those two, and we'll be done. Which is easier said than done. It's calculus, but it's calculus done not mathematically, but graphically. This is just describing everything I've said, so I don't need to have that anymore. So here we go. This picture has marked an origin. That's where we start our phasors. It has marked A, B, and C. B is the phasors where they add together at the screen. So if you go from O to B along the path that goes on M, so OMB, that tells you the electric field at a point on the screen. If you follow the arc length, that gives you E0, the total electric field that went through the slit. And what we want to do is to find how these relate. Because the total intensity has to do with the amount of light that went through, the electric field that went through the slit. The intensity at this spot is going to have to do with that OMB. So here is how we do our math. First, we have defined beta. Beta was on the previous slide. Well, 2 slides ago, actually, but I skipped one. And now this is using A, so A is the slit width. And so beta is the maximum phase difference for light that goes through one side of the slit compared to light going through the other side of the slit. The graph then is drawn with an angle that bisects OMB. Right? This line CA is bisecting it. And by the definition of a circle, we know that at all points the radius is perpendicular to the arc of the circle. And so this here, that's going to have beta, our maximum angle change for its angle. And it's going to be perpendicular to the radius. So I have an angle right here that's a right angle. By definition, of course, the radius is perpendicular to where I start. So I have a four-sided object, O, A, B, C. What's the sum of the interior angles for a four-sided object? Okay, so the sum of the interior angles has to be 360 degrees for a four-sided object. Now, if we look at what we have, if this angle here is beta, then by definition, this has to be the supplement 180 degrees minus beta. These two angles are 90 degrees, so then I can calculate this full angle here, which I will call, for right now, I will call it alpha, just to give it a name. So using this rule about the sum of the interior angles, I'm going to have alpha plus 90 degrees plus 90 degrees plus 180 degrees minus beta equals 360 degrees. Right? This is not stretching anyone's math skills. What's the first thing you would do?
Change alpha back to beta.
That would be a bad move. What were you saying, Sally?
Oh, just put all the numbers together.
Okay, Sally says let's move all the numbers across. So let's subtract 360 degrees from both sides. Because 90 plus 180 is 360. And we're left with alpha minus beta equals 0. Now we can do what Chad said. Now we can say, hey, look, alpha is equal to beta. Haha. Right? It wasn't a very hard derivation at all. And so since this alpha is beta and line CA is bisecting it, then that's what tells us, I'm going to erase the alpha now, that each of those two half angles is beta over 2. So now we are just about to the payoff moment. Does it feel like we're at the payoff moment? Yes, it does look like also we're pretty much at the end of the class period, so we better be. Now that we're at this payoff moment, let's look at the relationship between R and E theta 0. How can I relate R and E theta 0? Okay, I can make myself a little right triangle here. And what is the opposite side for that right triangle? That's the hypotenuse. What's the opposite side for this right triangle?
From what's beta?
From beta over 2.
Half of the sine.
Okay, so this side here is going to be E theta 0 over 2. And R is the hypotenuse. So that means opposite and hypotenuse relate through sine. So I have sine of beta over 2 is equal to E theta 0 divided by 2R. Now, R is really truly meaningless. R is not important to me. And so now I have a relationship between E theta 0 and beta. Beta is meaningful because it relates to theta, my viewing angle, and A, the slit width. But that R means nothing to me. But all is not lost, because I can also look at this arc and relate R to E0. What's the relationship between an arc length and the radius? That's the simpler definition. The arc length, which in this case is E0, is equal to the radius multiplied by the angle. So radius multiplied by the angle, for this entire E0, the angle is beta. That was real simple. Now I have two relationships. Let's just substitute that R is equal to E0 divided by beta and put that R into this. And so I'm going to have sine of beta over 2 is equal to E theta 0 divided by 2, and for R I'm putting E0 over beta. Take that and solve for E theta 0. So that means just multiply both sides by 2, E0 divided by beta. Or, as we like to write it, I think that was right. I have E0, yep. That's a 0 right there. So my electric field at some point at an angle theta is equal to the total electric field that comes through the slit times sine of beta over 2 divided by beta over 2. What's the last step? I need to square things to get it into intensity. And then I need to take the time average. But do I have any time in here? No. No, I kind of dropped that out when I went to the phasors. When I went to the phasors, I separated the time out. So I'm already there. My intensity is equal to intensity max times sine squared of beta over 2 divided by beta over 2 squared. Now we're out of time, so I won't continue with the derivation, but that does tell you you're going to get zeros anytime beta over 2 is equal to an integer multiple of pi. And you'll get your minima, well, you can go through and do it. We are out of time, so I'll see you in lab today.